Welcome back. Today we'll look at transformations of functions, and specifically we'll look at translations, reflections, and how graphs stretch and compress. So first let's look at roller coasters, which are so fun. I love roller coasters. And whenever engineers create roller coasters, they'll often have a model, which we're going to actually call a parent function. And then they'll use that model and create a transformation to build the roller coaster. So we definitely know that this is, actually both graphs are functions. Remember, functions pass the vertical line test. So wherever I draw a vertical line, it'll only pass at most one point. So every x has one y value. Okay, let's compare these two graphs. Now they're very similar. You can tell that they both have relative maximums. They both have one relative minimum. From last chapter, we can actually also compare their domain and range. So this domain for the parent function is -8 to +8. And it's the same for the transformation, -8 to +8. When I look specifically at points, I'm just going to draw this axis so I can see the graphs. So this point right here is -8, -1, versus this point is -8, +2. So you can tell that the graph, the transformation, is shifted up 3 units. And then when we look at how this is stretched, you could definitely see that this is stretched. Maybe this peak right here, that max is 4 units, versus right here, that's 8 units. So we'll say it's stretched vertically, and 4 times 2 makes 8. So let's get more precise with our vocabulary, but that's generally what we're looking at, is how things are shifting, moving, and stretching or compressing. Now, when we have a parent function, we often try to make sure it's shown with a letter. So here we have the parent function, x squared, which is a parabola. And so x squared is shown here in the blue. It's kind of hard to see. I'll zoom in. And the transformation is g of x, and that's the orange. And you can see that from this point to 4, it gets shifted down -3. And all the points here, this is 0, 0, this goes down 3. And so that transformation was -3. But what changed in the graph? So the shift was down 3, but when we look at the points that are impacted obviously are just the y's. That was 4, 2, 4. This is 2, 1. So we just subtract the 3 from the y. So when we subtract the 3 from the y, that's going to change the equation. So we know that f of x is the parent function, g of x is our new function. So let's write the new equation for g of x, since we already have the equation for f of x right here. So g of x is going to be the same graph as f of x, but everything is shifted down 3. So each of those coordinates went down 3. Now let's look at the domain. The domain for each graph is the same. So you could see the domain for the first graph is from -2 to 2, and they're both the same, right? It didn't shift left to right, it shifted down. So the domain for both is going to be the same. And I'm just going to put that in interval notation, -2 to 2. Now let's look at the range. So if the range, that's definitely going to change because we definitely see that this graph, the original, goes from 0 to 4 versus now this new graph goes from -3, and I'll make sure I mark it down here, -3 to 1. So I'm going to write this out, okay? So the original f of x, so for f of x, the range was 0 to 4. And then for g of x, the transformation is going from -3 to 1. So you could see that the y's have a difference of 3. Now let's go to the shift to the right and left. So here we have the graph still f of x equals x squared. That's our parent function. And it says the translation is going to be 3 units to the right. So 3 units to the right. So what happens is we have the points go from here. I'm going to move, we could use this point, -2, 4, and that gets shifted to the right 1, to 1. So that's going to be, we're going to add 3 to that equation. So, or to the x. So when we add 3, it's going to be f of x so let me just write these points here. So we have 2 to 3, -2, 4, changes to 1, 4. So this is our x, this is our f of x. And this switches to x, comma, g, x plus 3. So we're switching that x to x plus 3. Now when we have g of x plus 3, that's going to equal f of x. So I could say g of x equals f of x minus 3. So the equation is going to change for g of x to be f of x minus 3. Okay, so when we look at that domain and range, the domain definitely switches. The domain is going from -2 to 2 for f of x. But for the g of x, that's going to change, right? So this went from 1 to 5. So we could tell that all those values for the x are plus 3. Now the range on this one does not change. So all the graphs are between 0 and 4. So the range is going to stay the same. And we'll say from 0 to 4. Before we go on to the next example, I want to make sure everybody knows they can use their online book as well to follow along. So in your online book, you'll also see these as the assignments. You'll also be able to see these tabs. So maybe not every single tab that I see on my screen, but you will be able to see the interactive student edition. So when you go to the student edition, and you can click on the top, the interactive student edition, you'll be able to see the examples. And so for this first example, when we looked at the translations of graphs, you can actually see how the graphs move as you change the numbers. So on this graph, it has example here, but I'm going to use the sliders down here. So we could see that when we change X, you can see that all these points move, and you can see the graph in the picture. So 2, 4 translated to 2, 1 on g of x. So you can see that. When we go to the vertical example, you can see the same thing and use the sliders to see different points. Now let's look at reflections. Our original graph, f of x, is 2x minus 6. And you can see that the y-intercept is right here at negative 6, and there's another point up here, and that slope will be 2. So if I want to reflect this graph on the x-axis to form g of x, I'm going to use this x-axis as a mirror. So every point is going to be reflected on that axis. So I'm going to give this point the coordinate. It's 4, 2. And if it was reflected on the x-axis, the new point would be 4, negative 2. Now let's look at this other point down here, the y-intercept, 0, negative 6. If that's reflected on the x-axis, it's going to be 0, positive 6. So if I was going to draw this reflection, you notice that it intersects on the x-axis at the x-intercept. So it always crosses at that point like a mirror. So if I was going to look at any point, and we'll say xy, I'm just going to point this out here. So if this point is xy, we know that the x's stay the same, but the y's become the opposite. Just like over here, the x's stay the same, but it changed from negative 6 to positive 6. So for a reflection, all the coordinates are going to stay the same except for the y value. So I'm going to write this general rule that when you have a reflection on the x-axis, a point that's xy is going to change into x, let me put this here, reflection will be x negative y. And there's a lot of similarities. So the y-intercept of f of x, I'll put f of x is here and g of x. So that 0, negative 6 changed into 0, 6. That other point 4, 2 changed into 4, negative 2. So the y-intercept was different. It was the opposite, but the slope, you could see that instead of going, this graph went up 6 over 3. The blue graph is going to go down 6 over 3. So this new slope for g of x is going to be negative 2. So g of x is going to be negative 2x plus 6. Now let's look at the graph when it's reflected on the y-axis. So on the y-axis, which is right here, all of these points are going to be reflected like a mirror. And you can see already that this point 0, 6, 0, negative 6 is still going to be on the mirror, and so it'll be on the reflection. And this point over here, which is 4, 2, is going to be a reflection for negative 2. So if we're going to draw this reflection, you can see that that slope is going to be negative as well. So this slope is going down 6 and over 3. So this new function, g of x, will be negative 2x minus 6. For our last example, we're going to look at stretches and compressions. So here we have the absolute value of x, and you can see in the graph in the blue that this is the absolute value with a V shape. If we made a table of points and plugged in these points for x, we get these points for y. So for instance, negative 4, the absolute value of negative 4 is 4. And you can plot on the graph. The absolute value of negative 2 is 2. The absolute value of 0 is 0. And the absolute value of 2 is 2. And the absolute value of 4 is 4. Now we're going to look at a transformation. This original graph is considered the parent graph. Now let's go to the g of x. And the g of x is saying whatever the values are for the y, you're going to double them. So it's going to be 2 times f of x. So when we have the transformation, here's g of x, our y in f of x was 4. And we're going to double that for g of x, so it's 8. And you can see the points shifted from here to up here. Now let's look at the rest of the points. So the y value for f of x is 2. 2 times 2 is 4. 0, well 0 times 2 is just still 0. 2 times 2 is 4 like we did before, and 4 times 2 is 8. So that brings us back up. And you can see that it still has that shape. So let's compare the domains and ranges. The domain is still the same for both. It goes from negative 4 to 4. But the ranges change. So for f of x, the range was 0 to 4. It went up to 4. But for g of x, remember it was 2 times bigger. So g of x went from 0 to 8. So this is what we call as a vertical stretch. So transformation has that has the same shape, but is multiplied by the same factor, is called a stretch. And here you can see it's multiplied by a factor of 2 because it said the g of x was 2 times f of x. Now let's look at a compression. So for the function f of x, still our blue function, we're going to take g of x, and g of x will be f of x is equal to 2 times f of x. So what does that mean? It means that we're going to have to plug in 2 and then see what the value is on the f of x. So our new function, if I have 2 here, or negative 2 for our x, and I multiply that by 2, we'll have f of negative 4. And f at negative 4 is the absolute value of 4, or 4. Over here, I'm going to take negative 1, and I'm going to multiply that by 2, because it says multiply all the x's by 2. And when we plug in negative 2, the absolute value of negative 2 is 2. Well, 0 is nice because 0 times anything is 0, and the absolute value of 0 is still 0. Now we go back over to the positives. 1 times 2 is 2. And when we plug in f of 2, right, f of 2, that's going to equal the absolute value of 2 again, which is 2. And then we have 2 here, absolute value of 2 times 2, which is 4. That's f of 4. So now when I plot this new graph, I'm going to use these coordinates, negative 2, 4. That's right here. Negative 1, 2. It's right here. 0, 0 stays the same. 1, 2, 2, 4. So versus the vertical stretch, we're having a horizontal compression. And that means that we're having to shrink the domain. The domain is going to be different. So for f of x, the original was 4 and negative 4. So negative 4 to 4. But for g of x, the new domain is negative 2 to 2. Nothing changes with the range. The range is still 0 to 4. But it's really important for the compression that we see at this point, 4, 4 changes to 2, 4. So with a compression, the x value is actually divided by 2. So our original was xy, and then the transformation would be 1/2 xy. So that's a compression. So here we have this compression, and it's by a factor of 2. So another thing to remember for stretches and compressions, to be really careful, when the number is outside, it's times f of x. If it's greater than 1, it's going to be a stretch. If it's between 0 and 1, it's going to be a compression. It's going to flatten down, be like half or a third. And it's the opposite for the horizontal. So it's a stretch, right? It's going to get wider. It's a horizontal stretch when it's between 0 and 1, when the k or that number is inside. And it's going to be a compression if the k is greater than 1. Okay, here's another way to look at it when you have the values for a. But just remember, when it's a fraction, it's going to be wide. And when it's a number bigger than 1, it'll be a stretch.